Thank you. For the first 20 minutes of my talk, I just want to go over the list of co-authors with you. Let me begin with how do we get to know Egon, because everybody has a different story. Mine was kind of interesting because it was the 81 academic year. Egon was a von Humboldt scholar at the university in Cologne, and I was in Bonn. And at that time, Egon came to Bonn and gave a talk and presented a conjecture in that talk. And he kindly put that conjecture right in my wheelhouse. So 2 days later, I called him up in Cologne and I said, yes, Professor Balash, I think I've got a solution to your conjecture. And he said, oh, good, so do I. And he really didn't have it first. He worked it out. And so we got together and discussed it. And that led to something which I found was one of the most interesting aspects of my working with Egon over what I calculated to be approximately 39 years, which went very fast. But he tended to think of many problems differently from the way that other people thought of these problems. Have some of you seen that? And I think a large part of it is because so much of his development in operations research and mathematics was done under extraordinary circumstances where he was very much on his own and he just figured things out in his own way. And we would very often have these discussions which came around to that. The other thing that I found so impressive with Egon was the way that he had such an interest in applied problems. To a degree, I could say there were very few problems that I ever shared with Egon that he didn't like. He was interested in everything. And I remember when he told me he was saving the steel industry in Pittsburgh with his roll-around package of doing for the steel mills, I thought this was outstanding and an example of just the interest he had in a broad range of topics. Now, this thing I'm talking about here, first of all, I'm at West Point. And we've got a lot of co-authors because we've got cadets working on these projects, we've got junior faculty working on these projects, and the problem began even before that when I was still on in my last 5 years with IBM. Can you hear me okay when I talk here? Because I'll just talk quieter then. When I was with IBM, my last 5 years was spent setting up an organization with IBM's Global Business Consulting. And what it was called was the Center for Business Optimization. And what we did is we took analytics and optimization out to clients in a range of industries. One of the industries we were working with was actually the healthcare industry. And we were looking after a problem which was called massive fraud, which was the industry was facing. And this was a really big thing. This was an article which appeared in 2005, and the article claimed that at least 10% of the Medicaid dollars were spent on fraudulent claims. 20 to 30% were siphoned off by abuse. Who cares about that? Well, by the purest chance, one of our team members was in Albany, the capital of New York, with the governor of the state of New York, and as they were riding up in the elevator, the team member said, Governor Pataki, are you aware that last year your government spent over $4 billion, which were wasted because it was all fraudulent? Have a nice day, Governor. And he left. And somehow that captured the imagination of the governor, who thought this was something that could be looked into. Even for the state of New York, $4 billion is a big number. So what happened then was we got into it, and the whole thing was saying, are there ways we can do it that will actually find a way to deal with this fraud problem? And the more we looked at it, the more complex it seemed. Here's the situation, of course. This is why it mattered in the state of New York. The lower curve was showing the percentage growth in the budget. The red curve was the percentage growth in spending on Medicaid. Medicaid is the state health program which looks after insurance for people who are basically need financial support to be able to get medical help. And you can see it was just an enormous problem to the government or the state government, how do you deal with that kind of problem? This is a complicated problem, and here's why. this was the approach that we ended up using on it. And this is the general thing that's involved. Now, this is the reality of the complexity. The way it all begins is you look at this population of people that are submitting claims for reimbursement from Medicaid to cover the various expenses they claim to have incurred. And the first thing you do is you take this massive population of the state and you partition it into what are called peer groups. And these are groups of people that for various reasons you'd expect to behave somewhat similarly. So it may be because they're in similar geographic areas, it may be similar medical characteristics. So that led to a second step, which was saying once you've got these peer groups, then you can deal with each peer group individually. Why do we do that? Well, the reason is simply this. If you do that, you're hopefully going to get a stronger signal from an outlier in a peer group than if you're looking at the entire population. Sometimes you get outliers all over the place. They can sort of blend together and you don't see them. If any of you are interested, during coffee, you can ask me why my daughter got so interested in this project when I told her the state of New York was also using our software to detect people who had underdeclared their financial income. But that's another story. So what happened then is you form the peer groups, you look at the peer groups, you look for outliers, and at that point you've got targets, which we then say these are the targets for investigation. And what we do with those then is they go to the auditors, who then can decide which are the ones we go after. The really interesting thing about this sort of fraud detection is that they run it as a financial business where they're trying to generate more recovery from fraudulent claims than they're actually spending in getting that. So that, for instance, the domain auditor will validate the targets. Then there's a thing we go through where you estimate the cost and the recovery of each target to decide which ones you're actually going after. When I assured my daughter that in the tax thing that somebody who is working for a not-for-profit, fresh out of college, is not likely to be a target. She thought that was a good news. But so then finally, once you pick a target, you have to decide how do you go after them in the most cost-effective fashion. So it's complicated. What I'm going to focus on right now is this question of peer groups, and I'll tell you the reason for it. When I talked to the team about it, they were saying we do this clustering and form these peer groups, and I said, hey, that's pretty interesting. There are a lot of methods of clustering. What do you use? And they said, oh, well, we use a thing we call Condorcet clustering. And I said, cool, what's that? And they explained it to me. And I said, why do you use that? And they said, well, there's so many different types of clustering. It seems that the number of clusterings is almost identical to the number of data sets that people have found that show that each clustering is the better for their data set. And there didn't seem to be any standard way of measuring the quality of clustering. And that was what really got us interested in it, because I asked them about this and they said, no, it doesn't really matter. And they were right, because they said the important thing is that we're generating a good set of targets for the auditors. But the clustering problem is that when you've got a bunch of records and you've got a bunch of attributes and you are looking at them, first thing you'll do is you select certain attributes to use for clustering, and then once you've selected those, of course, the general idea you have is you want to define a distance or a difference between different records, and you'd like to have ones that are similar in those attributes you've chosen and have them in the same group. Good? Now, in order to help you are what I call a crowd, and I'd like to turn to the wisdom of the crowds. I'm going to show you several alternatives in clustering, and I'd like you to help me decide which is the better of them. Okay? Now, to make it easier, I'm going to represent the records by points on the plane, and what I'm going to then do is you can take the Euclidean distance as being an indication of the difference between the records. So if they're far apart, they're different. If they're close together, they're pretty similar. Are you ready for this? This is the work part. I mean, it's not going to be easy. All right, here we go. Here are some points. Don't ignore the colors for the moment. You can see we got a slew of points. On the left, we've got one set of clusters. On the right, we've got another set of clusters. The same set of points. How many like the one on the left better? How many like the one on the right better? And see, the others of you seem to be the ones that say, I can't tell. Is it fairly accurate? You're not doing very well on this. Well, let's try another one, all right? Are you ready? Here we go. Ha-ha. Ha-ha. How many like the one on the left better? How many like the one on the right better? Yes. We've woken people up. We're going to get this. How many think it doesn't make much difference? Now, I think I can give you one more. This is an interesting one. This is the pathological clustering situation, when you actually don't have little convex sets that you're trying to find, but you may have a ring of points. And if you give it to two different clustering methods, they came up with two very interesting alternative ways to cluster the points. What do you think? How many like the one on the left? The one on the right? How many don't think it makes a lot of difference? That's interesting. Okay, one more. Last one for now. All right, this one. Ready? This one. And the question, which do you like better? Yeah, this one looks, this one over here looks pretty good. Which one is better? The interesting thing is that, of course, it all depends on what you're going to do with it. In some cases, one is better. In other cases, another is better. But what we set out to do, and this is the mathematician in me saying, but surely we can define some kind of a measure of the goodness of clusterings. And if I have that measure, I can at least say, if you like that measure, then this would be the method that you would use. So that's what we wanted to do. There are inconsistent definitions of what a cluster is good. It's difficult to determine which of two similar clusterings is better, and most common clustering methods tend to create convex spherical shapes. And you can see it here. The one on the right is, no, sorry, yeah, if I say right, I'm looking at my screen. Yeah, the one on stage right. This is one that uses this, it tends to want to form these spherical blocks within it. This is one which says, I don't care about that. And the interesting thing about these examples is that the method, that the stuff that we developed was actually used, and it produced both of those depending on the parameter that was set, that would actually go from one to the other. So that's what I want to talk to you a bit about. Okay. So what we wanted to do was define a metric, or use a metric based on properties of good clustering. We wanted to use mixed integer programming then to find a clustering which optimizes the metric. This really startled the cadets, because what they were using at that time was we were trying different clustering methods on data sets, and then we would use this particular metric to see which one was doing a better job. And then I said, but you know, if you've got a metric like this, you actually could formulate it as an integer programming problem to find the best clustering of all. What would that clustering look like? And that led to an interesting branch of the problem. We then found a way that we could deal with this issue of the convexity. The method that we used is what's called, we call it the Condorcet metric. I didn't get permission from Condorcet to use that term, but I had first heard it from two researchers who are at the IBM Scientific Center, I think it was the one in Pisa, Pierre Michaud and Jean-François Marco Torcino, who were saying, well, if what we do is we have to say if points are similar, we'd like them in the same set, and if points are different, we'd like them in different sets. That can't be so hard. That seems like a good objective. The difficulty, of course, is that it can be quite conflicting. And how do you deal with that? You see, here's a set of points. And what we've, in that figure you're seeing there on the only one you're seeing behind me, it's got 5 clusters, each containing some of the points. And you'll notice in the lower left over here, there's a little r and a big R. Because what we wanted to do when we looked at clustering is we said, look, here's what little r and big R mean. If points are within little r of each other, like they're close to each other, and they're not in the same cluster, that's bad. And if they're really far apart, and they're in the same cluster, that's not good either. So these are the things it looks for. And what do we define by big and small? Well, little r says close together, big R says far apart. So if you're more than big R apart, you're not in the same cluster, that was a badness and so forth. Does that make sense? You get the idea of it. The thing about it is, that gives us, the good news is it gives us 2 parameters to tune. The bad news is it gave us 2 parameters we had to tune. But you can see what it shows there. So in this case, if you look at little r and big R like we drew it, you can see there that the points up over here are a couple of points in the same cluster, which are far apart. Here's a couple of points which are in different clusters, but are close together. That's where the problem arises. So what we said was what we'll do is we'll define a penalty, and the penalty is the amount by which the distance between those points is bigger than the thresholds that we had set in both directions. Make sense? Interesting. And that's showing example of how we get penalties in one case, penalties in the other case. And then we formulated and attacked it with mixed integer programming. Pause for my editorial comment. Early in my career, I love generating cuts for mixed integer problems and stuff like that. And generated a few in my day, I'll tell you. But well, I was working with a cadet on some, we were doing some Steiner problems, and I found I was getting really frustrated because I was adding cuts till I was blue in the face and it didn't work. And so finally I said, to heck with it. Tell Cplex, make an integer, go. And within a few seconds it had solved it. Because what's happened, of course, to IP and LP software, I know some of you have seen this, is that it's gotten so much better, and there's so much effective engineering that's gone into it, combined with the theoretical advances, that it's the path of low resistance is just give it a shot and see what happens. And that worked out pretty well. This formulation is kind of interesting. This first one is a formulation we often use for the max cut problem, where we're saying there, the unusual thing is these x, j, k variables are defined for each pair of points. And x, j, k is 1 if they're in the same cluster, and 0 if they're not. And so once you decide that you're going to have constraints for every pair of points, then you've got reflexivity, symmetry, and transitivity which go in. Once you've got that, you then simply have to minimize the sum of the penalties that are incurred by this, and you can write a pretty standard way of writing this down, which will force the PIJs to be set correctly, and you add up these penalties and it tells you what you got. Do you want more detail? You got it. Good? Yeah.
Can the number of clusters be a decision variable?
Yeah, well, actually, in this case, we do not set the limit of clusters. We do it entirely based on it. Now, it is possible to add that sort of condition to it, but we didn't do it. Okay. So what we found was interesting, because when we got to fairly big problems like thousands of points, what would happen is sometimes we run out of memory on these fine laptop computers which the federal government had provided for our cadets. On the other hand, and the method that we had also had this disadvantage in that it fell into this trap of always creating these convex sets. So these are examples. If you look above these figures, if you see one that says CC on it, like there's one says CCR equals 0.3, one says CCR equals 0.75. CC stands for what we call Condorcet clustering, which is you're using that method to find the clustering, and then it tells you the R values that we used. And as you change the R value, you get quite different results on it. but it always had this thing about putting clusters in convex forms. And also there were the memory and the timing requirements on it. So then, and then, this is interesting. There's a person named Leland McInnes who works for the Canadian equivalent of the NSA. And he's done some extremely interesting stuff. One of the things he did is he invented a clustering approach, which really motivated what we did. And this was an example of his algorithm. It's called DB-scan, applied to the data set that he had created. And he admitted candidly, he said, I carefully constructed this data set because I thought DB-scan would be a good job on it. And all the others do terrible jobs. Because when you look at it, and this is something over 2,000 points, but I think you can see that there's sort of an arbitrariness in the way things are cut. The other thing that his data set does is it's got a lot of sort of noise points, which you don't want to have in any cluster. And that's another feature you may have, is you don't require everything to be clustered. But we could take those, and the number, the CM below it, says these are the Condorcet measure of the quality of that clustering that was produced by different means. So there's k-means, the mean shift, agglomerative, which are standard, and then the DB-scan, which is Leland's. And the lower the number, the better. So in that way, it just looked like mean shift was actually the one that, by our metric, was the best. Leland's was only the second worst, so that's okay. But it was interesting, and it sort of supported this fact that the type of, the use you're going to make of it really does depend on the clustering method you may want to use. Now, when we set to deal with the next part, what we said was this: can we sparsify the network? Do you really have to keep all pairs of points in, or can we get away from that? And if we could get it by sparsifying, we would actually be able to speed up the operation because the number of variables and constraints would go down, which is a good thing. Could we do it in a way that it worked? And I was delighted when the previous speaker introduced Voronoi diagrams and Delaunay triangulations, because these provide a very interesting way of sparsifying a network. Why are they interesting? Well, first, they're dynamite figures. They're great. But the other thing, do you all know how a Delaunay triangulation is formed? You may say, isn't it just the planar dual of the Voronoi diagram? Yes, it is. And how's the Voronoi diagram formed? I think, isn't that just the planar dual of the Delaunay triangulation? Yeah, that's pretty much it. Here's how the Delaunay is actually formed. You've got a bunch of points. If you've got a bunch of points, there is a theorem that says any 3 points which are not collinear define a unique circle that passes through them. If that circle contains no other points, just those 3 on the boundary and none in the interior, then what you do is you throw in a triangle that joins those 3 points. And that's how you can construct a Delaunay triangulation. So that's where it comes from. At which point you say, that looks like it's a lot of work to construct. The interesting thing is that the computational geometers have been very helpful. First observation, because it's a planar triangulation, it's got at most 3n minus 6 points. The reason it's at most 3n minus 6 is because the outer face isn't triangulated. The surprising thing is it can be constructed in principle in order n log n. It does contain a minimum spanning tree on the points. It includes the convex hull of the points, nice features. One thing, though, is if you decide you want to build a Delaunay triangulation, go to the web and hunt, because you want good software, because there are numerical issues you run into when you're not quite sure whether this point is in the interior or not, and you want to be consistent in it. Now, for our use, we didn't mind if we were a bit sloppy. If we got a few that weren't quite right, it didn't matter, because we weren't trying to get a perfect drawing of it. We were just trying to decide which pairs we were going to look at when we computed penalties. I just put this one in because this is showing a case of a different situation. You see that with that circle that was constructed through those 3 points, do you notice there's one point that just snuck over the boundary into it? Which is why there wasn't a triangle that went in for those 3 points. So it's very specific. Now, the donut, which is that shape we've seen, here's the Delaunay triangulation, the convex hull, and a minimum spanning tree of that. And so our idea was then, why can't we go ahead and do a Delaunay triangulation of the, did I say that? Yeah, the last bullet I meant to mention, the construction of these Delaunay triangulations is polynomial in the number of points you've got, exponential in the number of attributes or the dimension of the space. So if you start going up 3, 4, 5 points that you're using in your clustering, it's going to take you longer to do. The good news is that even on data sets that have got hundreds of attributes, you don't try and cluster with 100 attributes. You try and pick the ones you think that are important and you work with that. So it's got some promising on that. So when we did it, here's the last eye doctor challenge, which do you like better? The one on the left was what we got when we did the Delaunay triangulation to define the pairs we were going to look at for penalties, and we ran with little r 0.17. The one on the right is when we ran the basic one without Delaunay triangulation using an r of 0.3. So you can start to see the fact that, and this was sort of a surprise to us, this sparsification helped you overcome one of these faults that you often get when you apply these sort of clustering methods. So I'm just going to finish off by showing you a couple of other examples we looked at. One of the ones that was sort of odd was you look at a list of United States cities. For each one you find the highest temperature ever encountered and the lowest temperature ever encountered, and you use those as your coordinates to cluster on it. It was really uninteresting, the results that it came up with, because it turned out that you get some very odd ones that went together. There were a few things that made sense, but it wasn't terribly illuminating. The one that we found, which was much more interesting, is one called the World Happiness Index. How many of you know about the World Happiness Index? Good. Would the rest of you be happy to know something about it? It was introduced in 2012 by the United Nations, and they were saying, the idea of happiness is something that should be measurable, and for a country, you should be able to determine its happiness. When they ran the World Happiness Index, do you want to guess who was the happiest country? Who said Switzerland? That's your hint. Yeah, Switzerland. Switzerland led the list, actually. What's surprising is that this index has really caught on. It's every year now it gets updated. And when I say it gets updated, it's not they just try and rerun the numbers, they change the factors and they change the things they're measuring. So what we did here is we said, what we'll do is we'll choose 3 of the attributes and do a 3-dimensional version of it. So these are 3 of them. One of the most important ones is this thing called wealth, which is the average GDP of the population. Are you a wealthy country or not? The second one we call family, and that's the one that says, do you have a family infrastructure that supports you? And do you feel if you have a problem, you've got people you can turn to? It's this sort of a community sense. The third one was the corruption. And you may think, why would you want corruption to be high? It doesn't mean that. High means you believe that if there's corruption, your government is going to try and eliminate it. It's sort of saying that the society will fight against corruption. And then we ran it. And this was the first one which we ran using k-means on the clustering. And so the colors that are the same show the countries that are that came out into the same clusters when we ran k-means on it. What do you think? Kind of interesting. The interesting thing about it was we found we ran the first stuff, if you looked at this and then you just look at wealth, and the GDP per capita, it really turned out this was dominant. And this was what was driving that index significantly. This is the 2015 numbers we were using there. We then did Condorcet optimization with Delaunay triangulation on it, and that was what we got. Clearly better, right? What's the little green country in the middle of South America? Poor Paraguay. And what about in Central America, the red country, is that Honduras? Yeah. Or Nicaragua? Yeah, it's, so we then set out to say, what on earth is happening? And some of these things seem very odd. Like, you could see some unlikely choices that would be the same. Like, why is South Africa and North and South America the same? And it turned out that what it was doing was looking at, if you look at this three-dimensional figure, it essentially, the clusters each were on a different slope of line that best represented the points in there. So if you had the same sort of balance as some other country, it would put you in the same cluster, even whether your numbers were quite different. So that was interesting where it went to. So what happens next? Well, one of the things we are looking at now is saying, can we actually find ways to speed this up? And can we accelerate it? Are there things we can do with the model that are going to make it work better? It's been an interesting project, and the thing I like about it is it does seem to combine the mathematical theory with what's a very real problem that we encountered. And that's my story, and I'm sticking to it.